All right, so we're going to go ahead and continue our example 8.7. So we need to use this idea of conservation of energy, and our energy here, our change in energy, is going to be equal to 0. So we should have some initial kinetic energy plus initial potential energy, and that should equal our final kinetic energy and our final potential energy. Okay, so we'll need to go ahead and look at each of these portions here. So we will have some sort of initial potential energy. So we have some height that it stays at. So we have mgh, whatever this height is. Okay. Then we have, let's see, initial kinetic energy. The particle is released from rest, it states. So we'll have the velocity equals 0. So our initial kinetic energy is 0 as well. Okay. For our final kinetic energy, we will have some sort of energy here. So we have 1/2 mv squared, and that is actually the velocity we are looking at, or the speed. Okay. And our final potential energy, if we say that this is our y equals 0, okay, so it goes down to that point. That means that our height now is 0. Okay, so we'll have 0 potential energy here. Okay, so now we have this expression here, and we can rewrite it as V equals, let's see, notice that our m's will cross out. We have 2gh, and m's cross out. So we have the square root of 2gh, and that will be our speed or our velocity. Okay. So what we need to do is find an expression for this h value here. Okay, so what is this height? So notice that the length of this string is 1 meter. Okay, and let's see. In order to find this h, we're going to have to do a little bit of thinking with some geometry or trigonometry. Okay, so let's see. We have, if it goes all the way down here, let me get a different color. If it goes all the way down here, right, this height is also going to be 1 meter. Okay, so we want to then find this value here. So what is this length? So if we can find this length, then we can find h. Okay. So let me go back to white. So we can analyze this triangle here. Okay, so this is going to be 90 degrees. And so we have a right triangle. We know the hypotenuse. So let's go ahead and solve for this side. So it'll be adjacent over hypotenuse. So we'll have cosine 30 is equal to adjacent side. So that's this side. I'm going to call it, I don't know, L divided by 1 meter. Okay. So let me write this down. I'm going to write it so that 1 meter is equal to L plus h. Okay, so we know that this is L here, this length. Okay, so from here I can go ahead and say that L then is equal to 1 meter times cosine 30 degrees which is then, let's see, cosine 30, 0.866 meters. Okay, so that's our L. Now our H then, we can go ahead and say H is equal to 1 meter minus that L. Okay. Or 1 meter minus 0.866 meters. So then H is going to equal 0.134 meters. Okay, so that's our height. That's this height here. And now we can go ahead and plug this in. Okay, so we have V is equal to 2GH square rooted. And we can plug that in. So we have 2 times 9.8 meters per second squared times 0.134 meters square root. So let's go ahead and plug that into our calculators. And we get the velocity is 1.62 meters per second. So that is our velocity or our speed, since we don't know which direction. Okay? Alright, so hopefully I didn't lose you guys on that problem. It can be kind of intimidating to look at this, but once you break it down, it makes a lot more sense. Okay? Alright, so let's move on to other forms of conservation of energy. So let's consider a particle in one-dimensional motion with some potential energy, U of x, and no non-conservative force, conservative interactions. Okay, so in this case, we'll have, remember we have E equals K plus U. So we can go ahead and solve that for kinetic energy here. Okay, so kinetic energy is 1/2 mv squared, and so we'll say that's equal to our energy. Our energy minus U, so that makes sense, right? Okay, then we can solve for our velocity, which is the same thing as saying dx dt. Okay, and that'll be equal to the square root of 2 over m times E minus our potential. Okay. We can then use this to solve for time, and that will be in a derivative form. Okay, so t is going to be the integral form. The integral from 0 to t of dt, or the integral from x naught to x dx over this little bit here, 2e minus u over m square rooted. Okay. So we'll be using this in order to either find the time or position of something, okay? So let's go ahead and do that. So we're going to use this potential energy, U of x equals minus E times x over x naught for E greater than 0, okay? We're using that in the last equation to find the position x of a particle as a function of time. Okay, so we want to find x of t, basically. Okay, so we will go ahead and start writing this down. T is equal to x naught to x dx over 2 times, E minus, U, which is minus E times x over x naught trying to make this as neat as possible, divided by m. Yes. Okay. And this is going to be in a square root. Okay. So, we can go ahead and do a couple things. First, I'm going to pull out some constants. So this should be, I'm going to say 2 over m in a square root. And then I'm going to have e times 1 plus x over x naught. Okay, and that's also in a square root. So then we'll have dx over 2e over m square root. I'm gonna pull out this x naught, so it's gonna look a little bit funny. So how you can do this is, say, multiply it by x naught over x naught, which is just multiplying by 1. Okay, so we're multiplying by 1 here. So then we'll have let's see. If I multiply, sorry, this is going to take me a second here. We'll have x naught plus x, right? No, this is just 1 still. Times x naught. Hold on, give me a second. I'm sorry. 1 plus x over x naught. Multiplied by x naught over x naught. Right. Right. That's right. Okay. Sorry, that took me a second there. Okay. So yes, we are multiplying by x naught over x. Come on. Pen. And so we are left with this here. Okay. X naught is just some constant, so we don't really, we can pull it out with this stuff. So really what we have is the integral dx of some constant. I'm just going to put a big C there. And then of 1 plus x to the minus 1/2. Okay, so this is essentially what we have. So we can take the integral of that, and we'll have our constant here, times, let's see, it's going to be 3, nope, the integral. So 2 over 1 times 1 plus x to the positive 1/2. Okay. Let me go ahead and continue this in the next video, since we are running out of time in this one.